With parametric equations, we are now able to do some calculus. So the first thing we're going to introduce is, what if I want to find a derivative using parametric equations? So suppose we have a set of parametric equations, x equals f of t and y equals g of t, describing a curve C. If f and g are differentiable, how do we find the slope of the tangent line at point C? We know the slope of the tangent line is, when we use derivatives, that is dy over dx. It is the derivative of y with respect to x. But we don't have a single function to say, here is my function y in terms of x, let me take the derivative. But thinking about these differentials as fractions, dy we could also write as the derivative of y with respect to t. And dx is the derivative of x with respect to t. And we do know how to find those. dy, or should start with dx dt, is gonna be that derivative of f, because x equals f of t. And dy dt is going to be the derivative of g. So if we are given two functions, we're going to take the derivative of the function of y and divide by the derivative of the function of f. So taking a look at our first example, we have a curve that is defined by the parametric equations x equals e t and y equals t e to the negative t. So if x equals e to the t, then dx dt equals e to the t. The derivative of e to the t is e to the t. If y equals t e to the negative t, then dy dt by the product rule is going to equal e to the negative t minus t e to the negative t. Or this is e to the negative t times 1 minus t. So finding dy dx is finding dy dt over dx dt. We have both those derivatives. Dx dt is e to the t, and dy dt is e to the negative t 1 minus t. This negative can send that e to the t down to the denominator, and we get 1 minus t over e to the t. And we have an equation within that parameter of t that will tell us the slope of the tangent line. So finding the equation for the tangent line at the point t equals 0, the tangent line equation is going to be y minus y naught equals m, which is the slope of the tangent line, times x minus x naught. We want to plug in t equals 0 into x, which is e to the t, y, which is t e to the negative t, and into dy dx, which is 1 minus t over e to the t. When we plug in t equals 0 into each of these, x naught is going to be e to the 0, which is 1. Y naught is going to be 0 times e to the 0, which is 0. And dy dx is going to be 1 minus 0 over e to the 0, which is 1. So we can fill in those pieces. 1 minus 0 equals 1 times x minus 1, or y equals x minus 1. There is our equation of the tangent line. We want to add on extra problem here, which is eliminating the parameter to obtain our equation in x and y. And that is eliminating the parameter from x equals e to the t and y equals t e to the negative t. Eliminating the parameter here is that y equals t e to the t negative t is also t over e to the t. We know this e to the t down here is x, but the t in the numerator is also something we can find in terms of x by taking the natural log. The natural log of x is going to be equal to t. So replacing out that information about x, we have the natural log of x over x is also our function. Y equals the natural log of x over x. Meaning what we have found is in part B, we have the equation of the tangent line when t equals 0, or the equation of the tangent line at the point 1, 0. Or x equals 1. So we can do a lot of the same things we have already done with parametric equations.